Hello everyone, thanks for tuning in. I'm Dmitry Duplyakin. I'm here to present this paper in data center performance. The only constant is change. This paper was accepted to CCGrid 2020, the last year's edition, and even a year later in this virtual setting, I'm happy to present this work. This was done in collaboration with my colleagues from the University of Utah and the Leiden University in the Netherlands. All right, I'm going to start by stating a well-known fact. Performance is not constant over time. As a motivating example here, I have a diagram from the work by Twitter. There's a package called breakout detection, and in this blog post, they talk about how they apply it. Specifically in this example, they use it for analysis of the CPU utilization time series. That's what we see in this picture. And as you can see, this time series consists of a series of steady states or segments where one goes to another through what's called a change point. The moment when that transition happens, that's a change point, and we see a number of them here. And I want to stress out the fact that it's true for more than just a CPU utilization trace like this. It's really true, the fact that performance is not constant over time, it's true for any benchmark that we run long enough. On any hardware, eventually, if we run it long enough, we will see change points like this. They don't have to be big, but they will likely occur over time due to some of the factors that we may not necessarily control. We may not know of them. They may be coming from certain system changes and whatnot, compiler changes, OS changes, things like that. And really, this phenomenon has implications for both system administrators who want to manage their infrastructure in a certain way, perhaps in an optimal way. And also, this has implications for experimenters using this type of hardware we're talking about here. For them, the key is to run their experiments during these steady states rather than through the change points, because really it will impact the results that they present. So, broadly speaking, this is a concern for these different groups of people who work on computing infrastructure, really of any kind. This is also relevant for clouds as well as high-performance computing centers and data centers more broadly. All right, here's my paper in one slide, type of slide. Here you can see several examples of the time series that we've gathered. You can see how we can segment them or find these change points. More specifically, we use the change point method that is coming from this 2019 stats paper. So I'm encouraging people to look at it. And in this work, the application for us is using this method for the big data set that we've collected on the system called Cloud Lab. I will talk more about it through my slides. This data set is really big, close to 7 million results collected on 1,600 machines for a period of 2 years and 9 months. So in this large data set, we've detected over 2,400 unique change points, and I will describe the patterns that we saw in these results. All right, so here's the outline for this talk, where I'm gonna answer the following questions. What performance numbers did we collect and study? I'll dive more into that topic. Then I will talk about the environment we've collected this data. I've already mentioned the Cloud Lab testbed that we used for this. I'll talk more about the method, and finally I will describe the results that we've gathered and what we can learn from them. All right, so in this study, the performance measurements were focused on the micro benchmarks, and there's a specific reason for that. The key here is that we wanted to capture the behavior of the system itself rather than individual applications. So this is sort of a lower level effort where the results that we collect and the findings in our work will eventually impact the analysis of applications. In this list of micro benchmarks, we have the NASA parallel benchmarks suite, NPB. For memory, we use things like Stream and also this Alex Reese's suite of benchmarks for SSE and AVX instructions, and for disk we use a utility called FIO. All of these things are fairly known in systems community, and there are plenty of papers talking about the results people collected using these types of benchmarks. All right, so the system under study is called Cloud Lab. It's a testbed funded by the National Science Foundation in the US. And it's not necessarily cloud. We think of it as a facility for making clouds. So it's a platform for experimentation on cloud computing. It's a distributed testbed for cloud computing and systems research. It's managed by 3 universities, the University of Utah, Clemson University, and the University of Wisconsin-Madison. What's important for this work is that this platform provides users, the experimenters using it, real physical hardware instead of virtual machines. And the reason why it's important is because by collecting the data in this manner, we have guaranteed that the results will not be impacted by other users using the same hardware at the same time. So that's the no interference fact here, which is critical for our work. And if you're curious to learn more about it, I would encourage you to look at cloudlab.us. That's where you can find the specs of the hardware available in the system and overall architecture, as well as you can find this paper, The Design and Operation of Cloud Lab, that we published in 2019. This paper has kind of an overview of the system design and the implementation. Another plug for our previous work is this paper that we published in 2018. It's called Taming Performance Variability, and this is really a precursor to this study where we used non-parametric statistics to identify outlier resources, and we found statistically dissimilar machines, among other things. We also thought this would be a paper focused on studying aging of the hardware, but at the end we ended up studying a number of analysis and presentation pitfalls, and in the paper we presented sort of lessons learned, hoping that we can help people steer clear of those pitfalls. All right, so I already mentioned the types of benchmarks we were running, these specific micro benchmarks that we used, and here I have a bit more information where you can see that we have over 2 million results for the CPU tests. We have 4.3 million results for memory tests, and then over 600,000 results for the disk measurements. What's important here is the notion of the configuration, which, so by configuration, we refer to a unique combination of hardware type, workload, and parameters. And as you can see, there are 590 configurations for CPU tests, over 1,000 for memory, and over 100 for disk tests. What's important here is that in this set of configurations, we studied different regimes, different sort of unique settings, where we have several examples here. So C220G1 and C220G2, so the hardware types. Then on the machines of those hardware types, we run single-threaded memory copy tests from stream, and in another example, single-threaded integer sort tests from the NPB. For those tests, what we can do is we can pin the computations to a specific socket if there's more than one on that type of hardware, and we can also control things like DVFS, dynamic voltage and frequency scaling. So these are just the examples of many configurations that we've sampled and studied in this work. All right, it's important to say a few more words about how the benchmarks are run. This is very important because we really care about sort of the quality of the data and trying to be methodical here, trying to make sure that we really capture an unbiased data set. So each run, a sequence of tests, takes place on a dedicated physical machine after a reboot. So here we're trying to capture the cleanest machine state possible. So the column in the middle, I believe I already covered that. We control things like CPU pinning, DVFS, and also multi-threading, trying to study all of the possible permutations of these factors. And then on the right, I briefly mentioned that every time we run a sequence of tests, it happens in the same order. There's ongoing work on this, but I'm not going to get into that right now. All right, in terms of data collection, this plot shows how many CPU results we've collected on a given day, and you can see that on a good day we collected almost 6,000 measurements, but at the same time there were also days when the platform Cloud Lab wasn't as available, and on those days we collected fewer or no results if the data collector was down. All right, so now let's take a closer look at the change point detection method. Here you can see again the examples of traces that we saw earlier. On the left plot you can see results coming from a single machine. So that's why there are only a few measurements there, like maybe 24 or so. And on the right we see a much larger data set. That's where the different values are coming from different machines of the same hardware type. And in Cloud Lab, there are about 10 or 12 different hardware types that we've studied for this work. So the method runs obviously for either. So the method that we've used is really agnostic to the source of the data or the type of the data we're studying. But I just want to point out that the latter, like looking at the larger sets of measurements, the ones coming from multiple machines of the same kind, that's what's being studied in this work. All right, as far as the method is concerned, it's called robust segmentation, and it's, again, like I mentioned previously, it's coming from this 2019 stats paper. I encourage people to look at it. And for the purposes of this study, what's important is that it's robust to outliers. That's what the authors claim and show in their study. It's tunable, and it's easy to tune. It's got a single parameter that controls how sensitive it is, so we thought that was valuable. It's also fast. It allows running the method on those larger data sets. And then we found an implementation in R, which we're able to use from Python through the RPy package. I also want to highlight that there is a survey of different change point detection methods, including various Bayesian techniques, and I want to encourage people to look at it for comparison reasons. All right, so again, on the segmentation side, robust segmentation, the method that we used demonstrates good performance, good segmentation, good change point detection results, and you can see several examples here coming from the original paper. I do want to also highlight here that with this method, we don't have to choose the number of change points. It'll be detected automatically, both their number and their locations. It's efficient and it's fast, and it uses the notion of this by weight loss, but I'm not going to get into that. More on it can be read in the original paper. All right, with this sort of with the introductory pieces covered, I have a few minutes to talk about the results. A little bit of notation here in the paper and in the slides. We'll be talking about the duration of the steady states. So those are the segments between the change points. We call the D sub n those durations, and C sub n is the magnitude of the relative change. That's the change in the means over the old value of the mean expressed in S percentage. So those are the things we looked at among other patterns. For the duration, here I have several histograms showing what we found, but I want to start with the example in the bottom left corner. We have an example time series with 2 change points, and those 2 change points really happened over the period of, I want to say, 14 months or so. So they're not that common. They can be common, and we found many change points in some traces, but in this particular one, I just want to demonstrate the fact that they are somewhat rare in some of these settings. So with that in mind, we can look at the histograms. We do see the small or tall bars for the very long steady states. Those are the points kind of on the right-hand side on each of these plots. And so for CPU, we had examples with over 500 days between the change points. For memory and disk, they're even examples with around 1,000 days between the change points. So that's really impressive. That speaks for the long-term stability of some of the hardware, like this Cloud Lab environment, which is again good for designed for the purposes of the experimenters, including people caring for this long-term stability. All right, as far as the magnitude is concerned, we have histograms capturing the values that we saw there for the relative change, and we should probably go in this order. So disk shows the largest changes. The range there is between roughly -30 to 30%. For the memory change points, it's mostly between -20 and 20%, and for CPU, it's even a bit smaller. It's -7.5% to 7.5%. So roughly almost all of the changes are in those ranges, with some exceptions, with some outliers. All right, so after looking at these high-level histograms kind of capturing the overall distribution of detected change points, we wanted to see how they align temporally. In other words, how change points occur for different benchmarks. Remember, this method that we're using is for univariate data, so for a single benchmark, for the results of a single benchmark recorded over time. You see 3 different examples in the left part of the slide. But we notice, obviously, that when the change occurred in one, it also occurs in the other one, and we wanted to kind of stack them. And that's what we did in this dashboard that we've developed. You can go to this URL and check it out. Also, the paper has more information about why we developed and what it shows. So, but it's really, in essence, it's stacking change points detected in different benchmarks with the idea of showing sort of getting into multi-benchmark change points, so to speak. All right, so when we did that, then we were able to clearly see some patterns in some kind of aligned simultaneous change points for different hardware types, including the case at the top here and the top row here, XL170 hardware type. It showed change points that occurred due to a BIOS change. Kind of an unexpected artifact here, unexpected finding, but that's what the data showed. We saw change points related to upgrades from one distribution to another, from one kernel version to another, and in the case with the bottom one, we see non-trivial changes such as 5.1% change in the memory performance. All right, I think I'm trying to wrap up here and just go through the rest quickly. So for steady states, we saw very steady, very stable results for disk performance. Again, spinning disks were more steady than some of the faster devices, as you would expect. The flash and NVMe devices are more complicated, and there are several examples of really steady CPU and memory time traces. All right. For the purposes of this work, we did a little bit of tuning for the method, how to tweak its sensitivity and yet capture most of the change points. So you can read more about it in the paper. I'm just pointing out that there's a specific value for the threshold that controls its sensitivity. Like we found a value that appeared appropriate to us. Finally, Open Artifacts, we have this dashboard running. You can check it out. And also all of the data and the tools that we've developed, it's all available as part of this repository. Final summary slide. The data and the tools are public, and our, we want to highlight the fact that change point detection can and should play a bigger role in such studies as studies of evolution over time for a facility or any component. It could be anything from networking device to a storage system to a facility to a compiler to really anything that for any artifact for which we care about its long-term stability and predictability. And also we can see examples of change point detection being used in reproducibility studies in combination with other tests that people already use, such as stationarity tests. I want to acknowledge our collaborators from the Netherlands who led the follow-up study. I encourage people to check it out. And I think that's all I've got. Thank you for listening, and please don't hesitate to reach to us if you have any questions or feedback. Thank you.